Good evening, everyone. I'm Nicholas Andrews, and today I'll be presenting my lab report for Physics 2211, Lab 3, which focuses on black holes. The purpose of this lab is to determine the mass of a black hole and the initial velocity vector required for a spaceship to slingshot around the black hole using GlowScript. The mass of the black hole we are working on is 1.4218 E34 kilograms, and the initial velocity vector of the spaceship is negative 0.9 E6, comma 10 E6, 0 meters per second. The models and equations we used in this lab report are as follows: universal gravitation, momentum principle, also known as Newton's second law. The components we're using are F-net parallel, which is along the motion of an object, which equals the change of magnitude of momentum, and F-net perpendicular to parallel, and it equals change in direction. We are also going to use the update formulas for these experiments. Experiment 1. In experiment 1, we tried to find the mass of the black hole based on the star's movements. The initial conditions were mass of star 2 e to the 30 kilograms, initial time 0 seconds, delta time 86400 seconds. Result: the mass of the black hole was 7.94977 E33 kilograms. Generating the ellipse path using functions like generate ellipse and generate trajectory Kepler helped create in the path for the star's movement around the black hole. We set up the scene with white background and define the star trail and black hole's positions. Constants like gravitational constant, mass of the star, and time intervals are defined. This loop calculates the net force on the star based on its position and velocity. Using Newton's second law, we can compute the change of momentum and force acting on the star. The mass of the black hole is then estimated from these calculations. In experiment 2, we aim to determine the initial velocity vector so the spaceship slingshots around the black hole. The initial conditions were mass of the black hole 1.4218 E34 kilograms, mass of the planet 9 E28 kilograms, mass of the spaceship 7 E10 kilograms, initial time 0 seconds, and delta time 1 second. The results were initial velocity negative 0.9 E6, 10 E6, 0 meters per second. We define the scene's background, objects like black hole, planet, and spaceship, and their initial properties. The system's properties and initial conditions. Set constants such as gravitational constant g and masses of the black hole, planet, and spaceship. Calculation loop. Calculate the gravitational forces acting on the planet and spaceship due to the black hole and each other. Update the positions and velocities of the planet and spaceship based on these forces. This loop continues until the spaceship completes the slingshot maneuver or crashes. What if tried to orbit the black hole? Instead of having a high initial x velocity to quickly go close as we can to the black hole, we should have a much lower initial velocity so we stay around the black hole. Conclusions. Errors. In experiment 1, letting the star orbit the black hole for a longer period could have provided more accurate data. In experiment 2, we used guess and check to determine initial velocities, meaning there could be multiple correct values. What does this mean? The rate of change of momentum is equivalent to the net force. This principle extends to the parallel and perpendicular components of the forces as well. Thank you for your attention. If you have any questions, I'd be happy to answer them.